Welcome to the deep dive. Today, we've got a pretty deep stack of sources to unpack, all focused on PCIe error management.
Yeah, it's a critical area.
It really is. And why should you care about this? Well, think about PCIe. It's basically the nervous system connecting the most vital parts of your machine, graphics card, NVMe drives, network cards, you name it, straight to the CPU.
Absolutely. It's the high-speed backbone.
So it's reliability. That's fundamental for system stability, performance, even data integrity. Understanding these errors helps you troubleshoot, figure out if your system's healthy, maybe even choose better hardware.
Right. It's not just for, the super low-level engineers anymore.
The material we have really gets into the weeds on the different error types and what they actually mean. So yeah, let's jump in and try to make sense of it.
Okay. So at its core, error management in PCIe is so vital because of the speeds we're talking about. Billions of transfers every second.
Crazy speeds.
Exactly. So keeping the data perfect on those links, especially between the CPU and, say, your GPU or main storage, it's non-negotiable.
And the sources seem to agree it's getting tougher, right? Higher speeds like PCIe 5.0, now 6.0 with PM4 signaling. It makes the physical connection, well, more sensitive.
Definitely. Higher frequencies, more complex signaling like PM4, they're just inherently more susceptible to noise, to signal degradation. It pushes the limits of the physical layer.
So the PCI designers had to think ahead.
Absolutely. The whole philosophy isn't just fixing errors after they happen, it's proactive. It tries to anticipate problems. That's why we see things like LCRC, ECRC, hardware replay buffers.
AER.
AER, exactly. And now forward error correction, FEC, which is a big deal in PCIe 6.0. It's all about layers of defense to catch things early.
That layered architecture must be central then. You've got the physical, data link, transaction layers, each doing its own job.
Yeah, that separation is key. It gives you isolation and efficiency in handling errors.
How so? What does the physical layer actually do for errors?
So the PHY layer is right at the bottom. Raw electrical signals. It deals with encoding, 8B10B, 128B, 130B, now LATs with PM4. So it's not just about speed. It helps with signal quality, too.
And link training. LTSSM.
Right, that whole complex handshake.
Yeah.
Get the link stable at the best speed. The PHY catches the really basic stuff, decoding errors, sync problems during training. And now with PCIe 6.0, FEC sits right there.
FEC. Forward error correction.
Yeah, it corrects minor bit errors super fast, like nanoseconds fast, before they even go up the stack. It's about low latency correction right at the source.
Okay, PHY handles the messy signal stuff. If it looks okay, it goes up to the data link layer.
Exactly. DLL is point-to-point, just between two connected components. Its job is reliable packet exchange on that specific hop.
How does it do that?
It adds CRCs, 32-bit LCRC for the main data packets, TLPs, 16-bit for its own control packets, DLLPs, and it uses sequence numbers for the TLPs.
Okay.
The big mechanism here is the FPCK NA protocol with a replay buffer. Receiver gets a bad TLP, bad CRC, wrong sequence number, it sends an add T, negative acknowledge. Transmitter, here's the NA, automatically resends the packet from its buffer. Simple, but really effective for transient glitches. The DLL also watches for problems with the replay process itself, like timeouts or the sequence number wrapping around too many times.
Got it. DLL makes sure things are good, hop to hop, then the transaction layer on top.
TL is where the actual work gets defined. Memory reads, writes, I/O stuff, config changes. It builds and consumes the TLPs carrying these requests.
Right.
It also manages flow control, making sure devices don't send data faster than the receiver can handle. Errors here are more logical. Malformed TLPs that break the rules, flow control issues, unsupported requests.
Unsupported requests, like asking a device to do something it can't.
Precisely.
Yeah.
Or completion timeouts, where you send a request and just never get the answer back. And optionally, ECRC errors.
ECRC, end-to-end CRC. That's different from the DLL's LCRC, isn't it?
Yeah, that's a really important distinction. LCRC is link by link, guarantees integrity across one hop. ECRC is calculated way back by the original sender, the requester, and only checked by the final receiver, the completer. It protects the packet across the entire path, even through switches.
So it can catch errors inside a switch that LCRC would miss?
Exactly. LCRC checks the links between devices. ECRC checks the data through devices. It's an extra layer for systems that need really high integrity.
Okay, so layers help catch errors low down. FEC or replay at the PHY DLL stops things escalating.
Precisely. Fixing it in hardware down low prevents it becoming a bigger problem that needs software intervention, which is much slower and might mean data loss.
Which leads to that main classification, right? Correctable, uncorrectable, non-fatal, fatal,
Yeah.
and advisory non-fatal.
Yep. That classification drives everything. How serious it is, what tries to fix it.
And to actually see these errors, that's where AER, Advanced Error Reporting, comes in.
Yeah, AER is the standard mechanism for devices to report errors in detail. AER-capable devices have special registers.
In their config space.
Right. Registers to log the specific error type, mask which ones actually trigger a report, set the severity, and crucially, a header log for uncorrectable errors. That log captures the start of the TLP that failed, which is super useful for debugging.
So the device spots an error, logs it, and tells someone.
It logs it locally, then sends an error message TLP upstream error core for correctable, earn and fatal, or error fatal, depending on the error and its configured severity.
Goes up to the root port.
Yep, the root port logs it too, and then critically it generates an interrupt to the operating system.
And the OS has drivers listening for this.
Exactly. Linux has the Ledger driver. Windows uses the WHEA, the Windows Hardware Error Architecture. They catch the interrupt, read the AER details from the root port, log everything, and coordinate with the actual device driver for recovery actions.
Sounds straightforward, but you mentioned firmware interaction can be tricky.
It can be. There's this handoffs, often using ACPI methods like OSC, where the firmware tells the OS what hardware features it can control. If the OS isn't granted control over AER, or if firmware tries to manage errors itself simultaneously, well, you can get messy reporting or missed errors. It needs clear ownership.
Okay, so AER tells the OS coordinates recovery. That summary table we saw seems to boil down. Correctable hardware fix, no data loss. Uncorrectable non-fatal, data loss for one transaction. Software recovery needed, link stays up. Uncorrectable fatal equals data loss, link unreliable, likely crash or reset.
That's the gist. And advisory non-fatal. Well, that's the odd one out, where an uncorrectable issue gets reported in a sort of informational, corrected way.
Let's dig into correctable errors first then. Sources say, hardware fixes them, zero data loss. Performance might take a hit, but the data itself is okay.
Right. And the fix is mostly hardware, usually in the data link layer.
The main fix being that DLL replay, ATNA.
Fundamentally, yes. Packet arrives bad, receiver encakes it, transmitter resends. That's the workhorse.
And FEC in newer PCIe versions.
Yeah, PCIe 6.0 onwards, FEC at the PHY layer is huge. It corrects bit errors before they even trigger a replay. Much lower latency impact.
Where do these correctable errors actually come from? Just random bit flips?
Some are just that random noise, maybe a cosmic ray hitting the silicon. There's an expected background error rate, the BER, which should be extremely low, like 1E12 or better.
Okay, so some baseline noise is expected.
But a lot comes from signal integrity problems. Issues with the PCB traces, maybe loose connector or a marginal cable, crosstalk between lanes, noisy power, anything that degrades that high-speed signal.
Physical path stuff. Makes sense.
Environment plays a role too.
Yeah.
Big temperature swings can affect signal timing. We saw that F5 Velos example.
Right, the train cold run hot thing.
Yeah, where they expect some PHY retraining or correctable errors as the system heats up. That's normal for them. EMI, electromagnetic interference, can also cause issues.
And just pushing the tech limits. Component aging?
Absolutely. Running at max speed, max lanes, like by 16 at PCIe 5.0, pushes signal integrity right to the edge. And components do degrade over time.
Oh.
And an interesting point from the sources, PCIe 5.0 uses precoding, which can sometimes turn a single bit error on the wire into 2 detected errors. Doesn't mean the link is twice as bad, just how the error appears after decoding.
So how does the hardware detect and fix these different things?
At the PHY, it's always checking symbol encoding rules. PCIe 6.0's FEC is constantly working on the incoming FLITs, correcting errors within maybe 2 nanoseconds.
Wow, fast.
Yeah, very fast. Equalization helps clean the signal first. Then at the DLL, the LCRC DLLP checks catch corrupted packets. Bad packet, dancer NAK dis or replay. If the replay itself fails repeatedly, you get replay timer timeout or replay number rollover errors.
What if the PHY problems are too much for FEC or equalization?
If the physical link gets really unstable, it triggers a deeper recovery state in the LTS at the link state machine.
LTSM recovery.
Right. It pauses data transfer for, maybe a microsecond, maybe longer, while the PHYs try to retrain, adjust equalization again, find stable settings. It's a much bigger performance hit than a quick replay.
Okay, so fast fixes, or a P-play, slower fixes, LTSSM recovery. How do we know this is happening? Where do we look?
System logs are key. On Linux, check DMESC. Look for lines saying severity corrected. They'll often specify the layer, like data link layer, and the type, maybe a replay timer timeout.
In Windows.
Windows Event Viewer. Look under the WA logger source. You'll find events for corrected hardware errors, often event ID 17.
Can we see it directly on the device itself?
Yeah, using tools like LPI-IV-VV on Linux, you navigate to the AER capability section for the device. There's a register called Correctable Error Status.
Ah, okay.
It has individual bits for receiver error, bad TLP, bad DLLP, replay num rollover, replay timer timeout, and that interesting advisory non-fatal error bit too. The root port also helps by logging which device sent the error message.
Any vendor tools that are helpful?
Oh yeah, many vendors have their own. For NVIDIA GPUs, NVIDIA SMIC PCI is great. It shows correctable errors, replay counter, and a really telling one, L to recovery counter.
L0 to recover.
Yeah, that counts how many times the link dropped out of its normal operating state.
Yeah.
L0 and had to go into that LTSSM recovery state we talked about. A high count there is a strong sign of persistent physical link issues.
Okay, so data is safe, but performance. You said it can take a hit. Is it noticeable?
Oh, it definitely can be. Replays add latency. LTSSM recovery adds microseconds of dead time, which kills bandwidth.
Right.
These things create latency tails, occasional unpredictable delays that can wreck performance for sensitive apps. In servers, high rates usually trigger BMC health alarms. The source has even calculated that a fast by 16 link near its error limit might see replays every second and a recovery every 10 seconds. That's not good.
So the million-dollar question, when can you ignore these corrected errors and when should you worry?
It's all about context and frequency.
Yeah.
A few isolated random errors, probably okay, especially on a desktop, just background noise.
Right.
Some vendors even give rough thresholds, like Dell saying maybe under 100 per lane per day is acceptable in some cases. And like the F5 example, errors during expected events like warm-up might be fine.
But when is it a red flag?
High frequency, a rate that's increasing over time, errors that keep happening after you try reseeding the card or rebooting. If you see performance issues or instability that seem to correlate, server environments are usually much less tolerant. And those specific counters, high replay counter, or especially L0 to recovery counter, those are definite warnings. Pattern and persistence matter.
What if you just ignore a high rate? Hardware's fixing it, right? So what?
The hardware fixes the symptom, the corrupted packet, but the high rate points to an underlying cause, bad signal, failing component, whatever. Ignoring that cause means it's likely getting worse. You risk it escalating until the hardware can't fix it anymore, and it becomes an uncorrectable error. You get chronic performance issues from all the retries and recoveries. It can mask a developing hardware failure. It might even shorten the component's life. Persistently high correctable errors are often the canary in the coal mine for bigger problems.
Got it. Early warning system. Okay, let's climb the ladder to uncorrectable errors. Hardware can't fix these. That sounds bad.
It is more serious, yeah. It means data loss or corruption happened for that specific transaction. And unlike correctable errors, these always need software, the OS, the drivers to get involved, log it, and try to manage the fallout.
And uncorrectable splits into non-fatal and fatal. What's the difference there?
It's all about the state of the link itself. Non-fatal means the transaction failed, data lost for that one request, but the link is still up and running for other traffic.
Okay.
Fatal means the link integrity itself is shot. It's unreliable, probably unusable, communication breaks down.
And you mentioned severity can sometimes be configured. A system designer can choose if a certain error is non-fatal or fatal.
Yes, AER allows that flexibility for some error types via the Uncorrectable Error Severity Register. So the same underlying issue might be treated differently depending on the system's design goals.
Software becomes really critical here then.
It's absolutely central. The OS and drivers have to handle the AER message, read the status registers, especially that header log, to see what kind of packet failed, log it, notify whoever needs to know, and try to recover or contain the damage.
Right.
And sometimes the impact depends on how well higher-level software copes. Like, can the storage system retry a failed write? Can TCP retransmit a dropped network packet?
Makes sense. Let's dive into uncorrectable non-fatal first. Transaction failed, data lost for that one, link still okay, software tries to recover.
That's the picture. What
Yeah.
causes them? Lots of things. Malformed TLPs, packets that just don't follow the PCIe rules, often a transmitter bug.
Okay.
Unsupported requests, URs, are super common. Software asks a device to access an address or function that doesn't exist or isn't allowed.
Like talking to the wrong address.
Kinda, yeah. Receiving a poisoned TLP that means something upstream already knew the data was bad, maybe a memory ECC error, and marked it.
Ah, so it's propagating known bad data.
Right. Completion timeout, CTO. You set a request, waited, no response. The target device might be hung, complete a report, CA, the device got the request fine, but failed internally trying to process it.
Okay, lots of potential transaction-level failures.
Yeah, also things like unexpected completions, ECRC errors if you're using ECRC, flow control problems causing overflows, ACS violations, internal device errors. And often, the root cause is actually a software or driver bug generating these bad requests.
How does the system try to handle these non-fatal ones?
Device logs it in its AER Uncorrectable status register. If it's unmasked and set to non-fatal severity, it sends that earn and fatal message upstream.
Root port interrupts the OS.
Yep. OS AER driver wakes up, reads the details, and then notifies the specific device driver for that piece of hardware.
And the driver tries to fix it.
It tries. Depending on the error and what the driver supports, it might retry the operation at a higher level, maybe try to reset just that function of the device, report an error up to the application, or if it's really stuck, it might just mark the device as faulty.
Does the OS reset the link automatically here?
Generally, no, not for non-fatal. That's a key difference from fatal. The AER driver usually leaves link recovery decisions to the specific device driver or higher-level policy for NFEs. Success really depends on how robust that driver is.
How do we spot these non-fatal errors?
Again, logs, Linux dmesg, severity uncorrected non-fatal often mentions transaction layer, lists the specific type like UR or CPO, and frequently includes the TLP header log data, which is invaluable.
Windows.
Event viewer, WAGA logger, usually error or critical severity, event ID 1. You often have to dig into the detailed data provided in the event. And yeah, in some bad cases, these could escalate to a WAGA BSR, but it's less common than with fatal errors.
Register's still useful.
Absolutely. LSPAI-VVVV. Check the uncorrectable error status bits, unsupported request char status, completion timeout status, etc. And crucially, check the uncorrectable error severity register to confirm why it was treated as non-fatal. Header log is right there too.
Vendor tools.
Yep, like NVIDIA SMI's non-fatal error counter.
What's the real impact? Data loss for that one transaction. Does it ripple outwards?
Ideally, no. It should just affect that specific operation, but that can still cause apps to err out, hang, or perform badly if they were relying on that transaction. The OS driver response tries to limit the blast radius. But if the device itself is critical, like your main storage controller, even a non-fatal error can have a big impact.
So, can you ignore these? Sounds like a bad idea if data was lost.
Generally, you should not ignore runtime non-fatal errors. Data was definitely lost or corrupted for that transaction. You need to know why.
Right.
The main exception we keep hinting at is certain boot time URs that get handled as advisory non-fatal, which are often harmless. But runtime URs, CTOs, malformed TLPs, that points to a real problem software bug, misbehaving hardware, maybe bad config. Frequency matters too. Are they piling up?
What if you do ignore them? Just hope for the best.
You risk silent data corruption, performance degradation, problems escalating to fatal errors or system crashes if the underlying issue gets worse. Makes troubleshooting future problems a nightmare. You could lose device functionality. Basically, the system becomes unreliable.
Okay, lesson learned. Investigate non-fatal errors. Now, the top tier. Uncorrectable fatal errors. Link integrity compromised, unreliable, crashes likely.
Yeah, this is the big one. It means the fundamental communication path is broken. What causes it? Could be severe data link errors that replay couldn't fix if they're configured as fatal.
Right, that configurable severity again.
Surprise link down, SLD, is a common one configured as fatal. Link just drops unexpectedly. Could be terrible signal integrity, power loss to the card, someone yanking a hot plug device incorrectly, or just catastrophic hardware failure.
What else?
Severe malformed TLPs, persistent flow control errors, receiver overflows, link training, just completely failing to stabilize.
Yeah.
Again, if configured as fatal. Critical internal device errors. And just plain physical damage, bad slot, cracked PCB, power rail failure.
Poison TLPs could be fatal too.
In some very high integrity systems, yes. They might decide that receiving known bad data is so critical that it warrants halting the system.
How does the system react to fatal? Sounds like it has to be drastic.
It is. Containment and reset attempt, but expect failure. Device logs it, sends error fatal. Root port gets it, fires a high priority interrupt, maybe an NMI.
NMI non-maskable interrupt. OS can't ignore it.
Exactly. The OS and firmware then try a system-level recovery, attempt a link reset, hot reset, maybe reset the whole component.
And the kernel itself panics.
Often, yes. Linux might broadcast that Ciccinelio frozen message telling drivers the path is dead. If the reset fails, or if the error is inherently unrecoverable, boom. System halt, crash, reboot. That's your Uncorrectable error, BHAS on Windows, or kernel panic on Linux.
Server management logs this too. Out of band.
Absolutely crucial. BMCs like IDVAC or IO log, fatal errors to the system event log, SEL. You can access this even if the OS is dead. Diagnosing fatal errors often means correlating OS crash dumps with these hardware-firmware logs. Sometimes the crash isn't just the initial error, but a failure in the complex recovery chain itself.
How do you spot a fatal error, besides the obvious crash?
Well, the crash is the main symptom. System hangs, freezes, reboots. In the logs, Linux to Macs will say severity uncorrected, fatal. Kernel panic messages often point to PCIe A error.
Windows BSOD.
The Win Uncorrectable error screen. Event Viewer has critical event ID 1s, but you need dump analysis usually.
Registered.
LSIFIU-VV. Uncorrectable error status bits are set, and the corresponding uncorrectable error severity bit must also be set for it to be fatal.
Yeah.
Vendor tools NVIDIA SMI show failure counts. Server cell logs, as mentioned. Sometimes systems won't even boot, getting stuck on PCI-related postcodes.
System impact sounds catastrophic.
It is. Link value, device gone, system hangs, freeze, crashes are expected. High risk of widespread data corruption because the link was unreliable before it died. Loss of critical services. That example of network throughput dropping to 0 is telling.
Can you ignore fatal errors? Or configure them away?
No, not really possible, and definitely not advisable. The system is designed to stop you. It forces a reset or halt because continuing in that state is too dangerous for data integrity. It's the call support now error.
Yeah.
Trying to suppress them is asking for disaster.
What happens if you somehow manage to ignore it?
Uncontrolled failure, cascading problems, massive data corruption, possibly silent at first, utterly unpredictable behavior. Eventually, it will crash hard or become unresponsive. It's the fail-stop principle. Better to stop cleanly, or crash, than continue corrupting things silently.
Okay, fatal, stop everything. Now let's loop back to that confusing one. Advisory non-fatal errors, ANFE. You said it's like an uncorrectable error reported as correctable.
Sort of, yeah. It represents conditions that are technically uncorrectable non-fatal events, usually unsupported requests, URs, or completer aborts, CAs.
Okay.
But the advisory part means they're often signaled using the correctable error path, using an error core message, and setting a special bit, advisory non-fatal error, in the correctable error status register.
Why do that? Why not just report it as non-fatal?
It's basically a way to provide information about these events without necessarily triggering the full OS driver non-fatal error recovery path, which might be overkill for certain expected events.
Okay.
So the underlying cause, like a UR, isn't corrected by hardware replay, but if its severity is set to non-fatal, the system can choose to report it via the error core path, just as an FYI, setting that ANFE bit. It can get tricky. Some devices might set bits in both correctable ANFE and uncorrectable UR status registers, like that TI bridge example. Reporting can be ambiguous depending on config.
What usually causes ANFEs?
The absolute most common cause, and usually totally harmless, is unsupported requests during boot time.
When the system is just figuring out what's connected.
Exactly. The OS or firmware probes for devices maybe asks about functions or memory ranges that don't exist on a particular device. The device correctly says unsupported request. If this is configured as advisory, non-fatal severity, it gets logged as an ANFE. It's just part of discovery, not a real error. AMD Xilinx docs explicitly say to ignore these boot time URs reported as ANFE.
So mostly noise during boot.
Often, yes. Completer aborts can sometimes be advisory too, but you can get runtime ANFEs.
After boot.
Yeah. If software, after the system is up, tries to access something invalid on a device, causing a UR, that's usually a software bug and needs looking into. And Intel mentioned ANFEs sometimes show up alongside a more serious uncorrectable error, sort of like a secondary symptom.
So handling and reporting really hinges on configuration.
Hugely. It's all about the AER register settings. Ideally, an advisory UCA sends error core and sits the ANFE bit in SESTA. But depending on masks and severity, maybe it sends earn and fatal instead. Or no message if AER isn't supported. You might see the ANFE bit in correctable status, maybe also the UR bit in uncorrectable status. Critically, for it to be considered advisory, the URCA severity must be set to non-fatal in the uncorrectable severity register. Then the correctable error mask controls if the error core message is sent. Vendor implementations vary.
How do we know for sure we're looking at an ANFE?
The key is that advisory on fatal error bit in the correctable error status, SESTA register. Using LSPI-JAFFE-VVV, you look for something like SESTA state-plot fatal plus flag.
Specific flag.
And you often see alongside the unsupported requester status bit being set in the uncorrectable status. Logs might just say corrected error, so you really need to check the registers to see if the ANFE flag is the reason. That LSPI example showing Carrera plus Sesta, non-failer plus lock, and Devsta unseparate plus together is the classic signature for a benign boot time ANFE.
Windows needs deeper event data analysis again.
Yeah, usually parsing the event ID 17 data. You often need to correlate multiple register values.
Can you give those examples again?
Sure. Boot time. OS probes function 1 on a device that only has function 0. Device sends UR, configured advisory, sets ANFE bit, maybe sends error core. Log says corrected. LECI shows the ANFE flag. Benign, clear the status, move on. Runtime. Driver bug tries to write to a reserve register on a card. Device sends UR configured advisory, sets ANFE bit. Log says corrected. LECI shows ANFE flag. Not benign, indicates a software problem needs fixing.
Right.
The TI bridge case showed complexity. UR triggered ANFE and NFE status bits, but sent earn Fitel due to config.
Yeah.
And the Intel case. ANFE appearing with another uncorrectable error means you need to look at the whole picture.
Ignoring ANFE's context is absolutely vital.
Context is everything. Those boot time URs from probing non-existent stuff, generally safe to ignore or just clear the status after boot.
Yeah.
Expected noise.
But investigate when.
Runtime ANFEs definitely investigate. Points to a software bug, bad config, something unexpected. Persistent or frequent ANFEs, even boot time ones if the rate seems high. Any ANFE that correlates with actual functional problems. Or if they show up alongside other, more serious errors. Advisory means the system doesn't panic, but it's giving you information to evaluate.
What if you mistake a runtime ANFE for a benign boot one and ignore it?
You could be masking real software bugs, drivers doing bad things. Could lead to weird device behavior, performance issues, makes diagnosing harder later. Could indirectly cause instability if the software handles the invalid access poorly. You might miss config errors or incompatibilities. It really relies on correct configuration and intelligent interpretation. Maybe just quickly recap a couple of those specific error types we mentioned.
Like malformed TLPs.
Right. Packet violates the PCIe rules. Could be a software bug making it, hardware fault sending it, or just severe corruption. Transaction layer detects it. Severity non-fatal or fatal depends on config. Impact is transaction loss or maybe a crash. Look for the malformed TLP status bit.
And poison TLPs and ECRC. One last time.
Poison TLP has the EP bit set, marked upstream because the data payload was known to be corrupt before it was sent over PCIe like bad memory ECC. It's a warning. This data is bad. Receiver sees the EP bit, sets poison TLP status, uncorrectable severity configurable, usually discards the data.
ECRC.
Optional end-to-end CRC. Sender calculates, final receiver checks, protects the packet through switches, catching errors LCRC misses. Failure is uncorrectable severity configurable, belt and suspenders for integrity.
Wow. Okay, so we've really gone from, tiny hardware fixed glitches all the way to system killing fatal errors.
Yeah, quite the journey. And we saw how the layers, AER, LCRC, replay, FEC, ECRC, even the tricky ANFEs all sort of interlock or sometimes behave differently based on configuration.
I think the biggest takeaway is just how different these errors are. Correctable, uncorrectable, non-fatal, fatal, advisory, non-fatal. That classification tells you the story. Impact could be anything from a tiny performance blip to a full crash or silent corruption.
And critically, ignoring errors, especially the uncorrectable ones. Just not a good plan. Hardware handles the easy stuff, but software has to step in for the serious ones. Your system's stability depends on it. Even corrected errors piling up are a warning, and non-fatal can still absolutely wreck your data or workflow.
So understanding these types, knowing how to check logs like DEMESG or Event Viewer, looking at AER bits with tools like LSPI, interpreting vendor counters, that gives you the power to diagnose what's actually going on with your system's health.
Definitely empowers you.
So thinking ahead, this gets really interesting. PCIe speeds are just going to keep climbing. 7.0 is on the horizon. Signaling gets more complex. How does error management keep up?
That's the big question, isn't it? Will FEC become even more critical, maybe multi-level? What about errors across chiplet interfaces using PCIe protocols? Will we see new kinds of advisory errors for even more complex distributed systems?
Definitely something to think about as you're managing your own systems. Thanks for joining us for this deep dive.